bit, weighted sum of two states, that is the state 0 and the state 1. And the weights are given by the coefficient A and B. Now these are called the probability amplitudes, and they decide how much percentage of 1 is present, how much percentage of the state 2 is present, that is the state 2, I mean the highest energy level, and whether it is only the lowest energy level or whether it is only the highest energy level or the next energy level. Now these probabilities A and B, now as you look at the equation, mod A and B are complex number. Complex number, it means they can be expressed in terms of a magnitude and an angle, phase angle. Now this phase is essential for different phenomena in quantum algorithm like coherence, entanglement, etc. Now the magnitude of A, that is square of the magnitude of the state 0 and the magnitude of the B square determines the probability of state 1. And as you can see, the equation is a summation of both the states. So let us suppose case 1. That is, I have only the lowest energy level, that is pure 0. So what will be the quantum state? Quantum state would be given by psi is equal to 1. That represent the magnitude. Magnitude of what? Magnitude of the state 0 plus 0. 0 is the magnitude of the highest level, that is the state 1. So it means I have only pure 0. Now the one condition should hold. Magnitude of A square plus magnitude of B square should be equal to 1 for this equation. Now case 2. Let us assume I have only highest excitation level or the state 1 or the bit 1. So what will be the equation quantum state? It will be the magnitude of the state bit 0 will be 0, but the magnitude of the bit 1 will be equal to 1. So this will be equal to pure 1. Now assume that I have 50% of state A and 50% of state B. So case 3, that is 50% of each of the state. Now if there is a 50% of each of the state, the quantum equation would be 1 by under root 2. This is the magnitude of which state? It is the magnitude of the bit 0 or state 1 plus 1 by under root 2 magnitude of the bit 1 or the highest energy level. Do you remember the probability of having the bit 1 is A square, that is 1 by 2, that is 50%. Similarly, probability of having the next high energy level in the state is mod of B whole square, that is 1 by under root 2 whole square, that is 1 by 2 is equal to 50%. Now, suppose I want 80% of bit 0 and 20% of bit 1. Then what will be the equation? The equation would be, the equation of the quantum state would be 0.8 of what? Of bit 0 plus 0.2 of bit 1. So what does this quantum state show? Quantum states show that we can have either the lowest energy excitation level or the highest excitation level, or both at the same time. That is, we can have the superposition at the same time. Now, if you read the hardware of quantum technology, these bits are realized through a LC circuit, a modification of a LC circuit. Now, if you can see what is the basic LC circuit, basic LC circuit consists of L and the energy oscillates between L and C. So the capacitor just charges through the inductor, which stores energy in the magnetic field, and then the magnetic circulates the energy back to the capacitor and charges it again. So in this type of circuit, the energy levels which are formed, they are at equal distance. That is, suppose this is the energy level 1, this is the energy level 2, this is the energy level 0, 1, 2, and 3. That is, equidistance means to make a transition from energy level 0 to the energy level 1, I need a amount of energy equal to h nu. Okay. Now, when a microwave pulse is given to the circuit, and if this microwave frequency resonates with the transition, that is frequency which is required to transit from 0 state to 1 state, then there will be a transition from the 0 state to 1 state. But there is certain disadvantage. As you can see, the transition between 1 and 2 also require the same amount of energy, h nu. So the microwave frequency will resonate with different transition frequency, and there will be multiple excitation in the circuit. That is, you can assume that you entered a room and the same, you entered a house and the key is same for different rooms. So with one key, you can enter the different rooms. Now, how this is overcome? So that I can have a unique transition. What is done is that this L is replaced by, you all know V is equal to L di by dt. This linear inductor is replaced by Josephson junction in parallel with the capacitor. That is, I have replaced the linear inductor by a non-linear inductor. This inductor is non-linear. Now, what is Josephson junction? So, you must have studied this junction is formed by two superconducting material joined by a thin insulating layer. This is the thin insulating layer. This is superconducting material 1. This is superconducting material 2. Now what happens is that here the electrons forms Cooper pair and they travel through the tunnel, that is through the insulation, to make a circulation of current throughout the circuit. Now what is the effect of this is that this result in unequal energy levels. That is, the energy band between 0 and 1 would be different. The energy difference between level 1 and level 2 would be different. The energy difference between level 2 and level 3 would again be different. So now, when a microwave of a certain frequency hit the circuit, it will excite only one state, that is the state whose frequency resonate with the frequency of the microwave. So in this way, I can isolate two states, any two states where I want the transition. Whereas in the conventional LC circuit, I cannot isolate the two states. So, and this is achieved, how it is achieved? It is achieved by the non-linear JJ junction, which results in unequal distribution of energy levels throughout the circuit. So if I say, if you look into the mathematics of this, maybe in some course you must have studied the energy function here is quadratic. That is energy function, it is of half capacitor energy plus inductor energy. Capacitor energy is half CV square and inductor energy is half Li square. Here the energy due to the capacitor, and this junction gives the cosine function of the energy, which results in unequal energy spacing between different energy levels. So to have an understanding of a qubit, we need to have understanding of the circuit, at least of the LC circuit. And of course, we need to have an understanding of the resonance. That is, as you all know, the transition is made possible by resonating the microwave frequency with the frequency of the energy band. So the question is, why in this course we need to study electrical network? Why resonance is critical for quantum technology? Now, I say in minimum word, resonance is needed for quantum technology for number one, manipulation. Number two, measurement. And number three, coupling of qubits. What do you mean by manipulation and control of qubits? Now, as you have seen, I hope there is a lag between the screen and the audio. I can resolve it. So I need to mute this. Let me know if we are able to resolve the issue. Now, the question was why we are studying resonance in this course of quantum technology. So, resonance is needed for the manipulation and control of the qubit. As you have seen that the transition from one state to the other state is made at the resonant frequency. That is when the microwave frequency resonate with the energy band frequency, and by controlling the amplitude and by controlling the duration of the microwave pulse, we can manipulate and control the transition from one state to other. In a similar way, since resonance circuits are selective in nature, now, since resonance circuits are selective in nature, what we can do is that we couple two qubits through an RLC circuit. What happens is that the coupling provides the selective frequency so that the two qubits can be selected. The LC circuit is also used, the LC resonator is also used for the measurement of the output of qubit. That is, if a certain frequency is measured, if it is equal to the resonator frequency, it means that the qubit has no effect on that resonator. However, if the qubit has an effect on the resonator, depending upon its state, whether it is 0, whether it is 1, or whether it is a combination of 0 and 1, the resonant frequency of that measurement LC resonator will deviate from the resonance frequency, and then we can measure at what frequency your qubit is working. So, the knowledge of the circuits and hence the knowledge of resonance is essential for realizing the hardware of the quantum technology, for understanding the process of the quantum technology. So, what is resonance? Resonance occurs when the driving frequency is equal to the natural frequency of the system. Now, when the driving, we will see how it happens. When the driving frequency is equal to the natural frequency of the system, then it results in maximum energy transfer. It results in enhanced signal amplitude, and we can also manipulate the coherent state of a qubit. How we will come to this? So this is basically the resonance condition. That is, the driving frequency should be equal to the natural frequency of the circuit. Now let us consider a signal, maybe a voltage or maybe a current. Let us consider a sinusoidal voltage source V is equal to Vm sine omega t plus alpha, right? Now, you all must have studied the Euler's theorem for the complex plane. That is, this is a real axis and this is the imaginary axis. There is a sufficient lag between the screen and my writing. So this is the Euler's theorem. This is the real axis and this is the imaginary axis. Now let us consider a vector at an angle alpha. That is, we can say this is equal to AJ alpha. Now, as you all know, EJ alpha can be written as cos alpha plus J sine alpha. Now, as you can see, sine component is the projection of this on the imaginary axis. So, the projection of e raised to the power j alpha, sine, the imaginary component, the coefficient of imaginary component is the projection on the imaginary axis. So, e raised to the power j alpha, the magnitude of this is always equal to 1. Cos square alpha plus j sine square alpha, it is always equal to 1. Now, what we do is that let us consider a sinusoidal voltage signal V is equal to Vm sine omega t plus alpha. Now I can write this as this is equal to the imaginary part of Vm e raised to the power j omega t plus alpha. Already we have seen this. And the same can be written as imaginary part of Vm e raised to the power j omega t into e raised to the power j alpha. So, now we all know the maximum voltage is equal to Vrms e raised to the power j omega t e raised to the power j alpha. And it is equal to imaginary under root 2 Vrms into e raised to the power j alpha e raised to the power j omega t. And this will be equal to imaginary part of Vrms e raised to the power j alpha into e raised to the power j omega t into under root 2. So, look at this component. Vrms e raised to the power j alpha. Should go there only. It is so much of lag. Nobody can understand like this. Not able to see your writing. It is all there. I'll go there only. You mute this camera.
ठीक है यहाँ से move कर लीजिए करो
Hmm. Unmute. Dear
Dear
participants,
participants,
since I
since
could
I
see
could
that there
see
is
that there is a very much lag between the screen and between writing, we are just changing the internet connection so that we can reduce the lag. Give me 2 minutes. Okay. So we are starting with again with a little portion. We have changed the internet connection and I hope now we can limit the lag between the screen and the writing. So I was starting with the Phasor representation of the sinusoid. Now look here, you all must have read the Euler's theorem. What does it say? It says if I have a complex plane sigma and j omega, then this e raised to the power j phi can be represented as a vector at an angle phi with respect to the real axis. The magnitude of e raised to the power j phi is always unity. That is, e raised to the power j phi is equal to cos phi plus j sine phi. That is, the magnitude of e raised to the power j phi will always be equal to unity and it can be represented by a vector whose length is unity and whose projection on the x-axis is equal to the cos phi and whose projection on the phi axis or imaginary axis is sin phi. So we will use the concept to write the sinusoid phasor form of a sinusoid. Now suppose I have a sinusoidal signal Vt is equal to max sine omega t plus alpha, right? Now I can write it like this. It is equal to the imaginary part of Vm. As we have seen, sine omega t is the imaginary part of e raised to the power j phi. So I can write it is the imaginary part of e raised to the power j omega t plus alpha. And if I expand this, so it can be written Vm e raised to the power j omega t into e raised to the power j L. And the maximum magnitude can be written in the form of RMS voltage. Vm is equal to Vrms e raised to the power j omega t into e raised to the power j alpha, right? Just manipulating the expression, we can write E imaginary equal to Vrms e raised to the power j alpha into e raised to the power j omega t and we can bring it. Now look at this expression. V sinusoid, the frequency would be 50 hertz. And if I'm working with a 60 hertz signal, it would be 600. All relating with the maximum voltage. So this Vt, the instantaneous voltage in phasor form by a capital letter with a cap on it, and it should have a magnitude that is The magnitude is equal to the RMS value of the phasor, and it would have an angle, and the angle is equal to e raised to the power j alpha. That is, I can write it like this: VRMS angle this. As you can see, this has an angle. That is, if I want to represent, this is your real axis, this is your image axis. The length of this arrow will be equal to VRMS. Okay, and the angle from the real axis will be equal to alpha. So basically, this voltage has been represented in the form of a vector having a magnitude and an angle. But look at this factor EJ omega t gives an angular rotation to the frequency of omega. So it is rotating at an angular frequency of omega. So what is a phasor? Phasor is basically a rotating vector. Now, in a similar way, phasor has a magnitude to omega. Suppose O So now what is a phasor? As I have already said, this term e raised to the power j omega t gives the rotation at a frequency omega. So what is a phasor? Phasor is basically a rotating vector. It is basically a rotating vector. That is, if I write V is equal to instantaneous voltage, Vt is equal to Vm sine omega t plus alpha. Now, this same instantaneous voltage can be represented in the phasor form as V. Magnitude, magnitude of the phasor can be taken to be the maximum voltage or the RMS voltage, but in most of the references we take the RMS voltage as the magnitude of the phasor and the angle alpha. Now suppose I have two signals, Vt is equal to Vm sine omega t, and I have other signal It is equal to Im sine omega t plus alpha. Now, how to represent these two signals in a phasor form? So, for Vt, phasor V will be equal to the phasor V will be having a magnitude and an angle. So its magnitude will be equal to the RMS value. So V is equal to V, RMS value we are writing in this form. RMS value is equal to V and angle is 0. And what about the phasor I? Phasor I can be written as the RMS value I and an angle alpha. Now this I and this V are the RMS value of the voltage and current respectively. Dear participants, there are some issues with the network today. We are trying to coordinate so that we can give you maximum. The page is again, the network has gone. Just a message float. Now starting with the So starting with a very basic circuit, that the resistive circuit. Now let us consider a single resistance and a sinusoidal voltage source Vs is applied across a resistance. So in instantaneous term, I can write the equation of the voltage as Vs is equal to under root 2V sine omega t. Since the driving force is a sinusoidal will current will flow through it, and let the current be under root 2 I sine omega t. Now we need to find out the voltage across, the relation between the voltage across the resistance and the current through the resistance. Now let us go by the Ohm's law. The instantaneous voltage VR will be equal to the current and the resistance R. So I can write the instantaneous voltage across the resistance as under root 2 IR sine omega t. Now this is the current through the resistance. This is the IR and this is the final voltage across the resistance. This is VR. So these are in the instantaneous form. It is so much of lagging is there.
Now look at equation number 1 and look at equation number 2. Now what we want to do is that we want to write both the equation 1 and equation 2. That is, I want to write both the current and the voltage in phasor form. So let us write the current. So phasor IR, it will have a magnitude. What will be the magnitude? Where magnitude will be equal to the RMS voltage of the current. What is the RMS voltage of the current? It is I. What is the angle of this phasor? The angle of this phasor is 0, since omega t plus 0. So angle of this phasor is equal to 0. Now come to the look at the equation number 2. Now at equation number 2, I want to write the phasor voltage across the resistance VR. So for a phasor, I need a magnitude and I need an angle. So what is the magnitude? It is the RMS value of the voltage across the resistance. So it is VR. And what is the angle? It is sine omega t plus 0. So the angle is already 0. Now, when we compare phasors or when we draw a phasor diagram, what we need is that we need to decide the reference phasor. Now, the choice is yours. You can take current as a reference phasor or you can take voltage as a reference phasor. Once the reference phasor is decided, all other phase angles are defined or shown with respect to the reference phasor. So let us take the current as a reference phasor. Now, current in phasor form is I0. So let us draw the reference phasor. This is the current. So the length of this phasor will be equal to the RMS value of the current. And since the angle is 0, this phasor lie along the horizontal axis. So this is phasor IR. Phasor IR is equal to I angle 0. Right? Now we have to plot the phasor VR. So let us plot the phasor VR. Phasor VR again, it is also lying along the angle 0. So the phasor VR will be along the same direction, but the length of VR is equal to IR into R. So it will be also along the horizontal axis. So this is VR phasor, which is equal to VR angle 0. So looking at the phasor diagram, both the voltage and the current are in phase with each other. That is, across the resistance, the phasor, there is no phase displacement between the voltage and the current through voltage across the resistance and the current through the phasor, and both are in same phase as shown in the diagram.
A request to all the participants, kindly go to the YouTube link which is shared. There the lag is nil. The lag is more on the WebEx platform. So if you look at the instantaneous voltage across the resistance, it is 2 VR sine omega t, and the current we have already taken as under root 2I sine omega t. Now these are in phase. What does it mean? That the peak point of IR and VR will be at the same place. The 0 point of zero crossing of VR and IR will always be together. Now look at the phasor. The phasor representation of the current, I is equal to I angle 0 and VR is equal to VR angle 0. That is, there is no phase displacement between the current phasor and the voltage phasor. So if I draw the current phasor, that is the current through the resistance, as IR is equal to IR angle 0, and then if I want to draw the phasor VR, the length of the phasor VR will be greater than the phasor IR, but they are along the horizontal line, that is both the voltage and the current through the resistors are in same phase. Now, let us define the impedance of a purely resistive circuit. Now, how does the impedance is defined? Impedance is defined as the ratio of the phasor VR and the phasor IR. Now, as you can see, phasor VR is VR angle 0 degree and phasor IR is IR angle 0 degree. So, the magnitude cancel and we get only ZR is equal to R. That is, the impedance of a purely resistive circuit is ZR is equal to R. Now, similarly, in a similar manner, we can see the inductor. Let the current going through the inductor is sinusoidal with the RMS value of I. So it can be expressed as I is equal to under root 2I sine omega t. Now if I write the expression for the instantaneous voltage, VL is equal to L di by dt. And if you solve it, you will find the expression for voltage across the inductor to be under root 2 omega Li sine omega t plus 90 degree. Now let us write both the current through the inductor and the voltage through the across the inductor in phasor form. So phasor IL. So phasor IL will have a magnitude. What is the magnitude of the phasor IL? It is equal to the RMS value of the current, and the RMS value of the current is I. What is the angle of this phasor? The angle of this phasor is 0 since sine omega t plus 0. So I will write here 0. Now look at the expression of the instantaneous voltage. Now I want to write the phasor expression for voltage across the inductor by looking at the expression of the instantaneous voltage. So again, this phasor will have a magnitude and this phasor will have a angle. So the magnitude we are taking to be the RMS value. So RMS value of VL will be omega Li. I hope you remember the relation. Maximum value is equal to under root 2 times the RMS value, and every sinusoidal expression is written as Vt is equal to Vm sine omega t plus alpha. So comparing both these equations, you can see that the RMS value is omega Li angle 90 degree. Right? Now, there is a very important operator defined in this circuit as the operator J. Now, what is this operator J? Operator J is defined as one angle 90 degree. That is, it has a magnitude of 1 and it has an angle of 90 degree. What does it mean? It means that if this operator is multiplied to any phasor, it will rotate that phasor in by 90 degree in anti-clockwise direction. Please take care. The anti-clockwise direction is taken to be a positive angle. So I can write the, suppose this is a phasor A. Okay. This is along the horizontal line. Now I want to draw the phasor JA. Now what if I want to draw the phasor JA? What does J means? That is the magnitude of this phasor remains same, but it is rotated by an angle of 90 degree anticlockwise. That is, this will be equal to JA. That is, the magnitude will remain same, but the phasor is rotated by an angle of 90 degree. So VL is equal to, I can write J omega L I. That is, one angle 90 degree has been replaced by I. And I can write VL is equal to XL into I. What is XL? XL is equal to J omega L, and it is called the impedance of purely resistive circuit. How this is called the impedance of a purely resistive circuit? See, Z is equal to, the impedance is always the ratio of the phasor voltage and the phasor current. So Z is equal to ratio of phasor V and phasor I. Phasor V is the omega Li 90 degree. I is equal to I angle 0. So ZL is equal to omega L 90 degree. Angle 90 degree can be replaced by the operator J. So it is equal to J omega L. Now, if I want to see the phasor relationship between the current through the inductor and the voltage across the inductor, so we have to decide the first the reference phasor. So let us take the reference phasor to be current. Okay. Now the reference phasor, we prefer to draw the reference phasor across along the horizontal line. It is not a thumb rule. You can draw reference phasor in any direction, but once you have decided the reference phasor, you have to draw the other phasors with respect to the reference phasor. So IL was equal to I angle 0. So the length of this phasor will be equal to the RMS value of the current, and it is along the horizontal line. Now look at VL. What was VL? VL is equal to J omega L I. That is, this I phasor is multiplied by an operator G. So what will be the direction of VL? The direction of VL will be the direction which is 90 degree anti-clockwise to I. Do you remember? J acts as an operator which rotates any phasor by an angle of 90 degree in anti-clockwise direction. So if this is the if this is the direction of I, if I am seeing the direction of VL as J into I, it means this direction rotated 90 degree counterclockwise, and this gives the phasor VL. The length of this will be equal to J omega Li. So, as you can see, in anti-clockwise direction, phasor IL is behind the phasor VL. That is, IL lags VL by an angle of 90 degree. How do you define lag or lead? Lag or lead, it's decided by moving in the anti-clockwise direction. Suppose if I am moving in a circle, if I move in anti-clockwise direction, if I am behind somebody else, it means I am lagging that phasor, or I am lagging that person. Now, was the case when I have selected I as a reference phasor. Now, if somebody can say, ma'am, what if I want to select VL as a reference phasor?
So if you want to select VL as a reference phasor, can you see what is the phase difference between VL and IL? Look here. This is IL and this is VL. The phase difference between VL and IL is 90 degree. That is, suppose if I take VL as a reference phasor. So this is my VL. Okay. Now look this. VL, the current IL, the direction of current IL is minus 90 degree behind the current direction of VL. The angle here is 0, the angle here is 90 degree. So the direction of IL is minus 90 degree behind. That is, with respect to VL, minus means counterclockwise. I will move clockwise. Anti-clockwise is positive direction and clockwise is negative direction. So IL, since IL will be, the angle will be minus 90 degree with respect to the voltage. So it will be like this. This will be your IL and this is your angle. I have shown the arrow of the angle to be at the minus 90 degree. So VL, that is IL, lags the voltage. Current through the inductor lags the voltage by an angle of 90 degree. In a similar way, you can say that the voltage through the inductor leads the current through the inductor by an angle of 90 degree. That is, for defining lagging or leading, you have to define the reference phasor and then you have to talk which term is lagging with respect to what. So there is no thumb rule that lag angle would always be a negative, lead angle would always be a positive. No. Lag and lead angle, the sign convention depends upon the reference phasor. What reference phasor you have taken. So, if I have taken IL as the reference phasor, I can see VL is ahead of IL in counterclockwise direction by an angle of 90 degree. That is, VL leads IL by an angle of 90 degree. In a similar manner, we can see the capacitor circuit. Let the current through the capacitor circuit be I is equal to under root 2I sine omega t. We know the relation between the instantaneous voltage through across the capacitor and the instantaneous current. Vc is equal to 1 upon c ic dt, and here we get the expression for Vc when we solve it. Due to limitation of time, I'm not going through the derivation. It is a simple basic mathematics. So I have two phases. Again, see one thing. I have two phases. One, I have to write the current through the capacitor. If you see the current through the capacitor in phasor form, I have a magnitude. What is the angle? Omega t plus 0. So the angle is 0 degree. Now look here. If I want to write the voltage across the capacitance, the phasor voltage. So phasor voltage will have a magnitude. The magnitude is taken to be the RMS value. So the RMS value is I upon omega c. What is the angle? Sine omega t plus of minus 90 degree. That is, the angle is minus 90 degree. Now, I've already told you that J is an operator with a magnitude of 1 an angle of 90 degree. So, I can write the same expression as I upon omega c minus J. Okay. Now, I multiply numerator and denominator by J, and J square is equal to minus 1, and therefore VC will be leading to I phasor I upon j omega c. That is phasor I upon xc. Now xc is equal to j omega c. Now let us draw the phasor diagram. So the phasor current was IC is equal to I angle 0. So IC is drawn along the horizontal axis, and the phasor voltage VC is equal to 1 upon omega c minus 90 degree.
minus 90 degree means with respect to the reference phasor, I have to move in clockwise direction, and this is my clockwise direction. And you see that phasor VC is lagging the phasor IC. That is, you can say that across the capacitor, the voltage across the capacitor lags the current through the capacitor by an angle of 90 degree, or you can say in other words that the current through the capacitor leads the voltage across the capacitor by an angle of 90 degree. So these are the basics relationship between the resistor, basic component, passive components of the circuit R, L, and C. So in R, as you can see, both VR and IR are in phase. Across inductor, the voltage across the inductor leads the current through the inductor by an angle of 90 degree, as you can see over here. And across the capacitor, you can see that the current through the capacitor leads the voltage through the across the capacitor by an angle of 90 degree. That is, the one who is ahead in anti-clockwise direction leads, and one who is behind in anti-clockwise direction lags. So you can say any way round, that is, you can say that the current through the capacitor leads the voltage across the capacitor by an angle of 90 degree, or you can say that VC lags IC by an angle of 90 degree. Now let us move ahead and let us see what if I keep on combining these terms. So let me combine these terms. Let me combine R and L. Okay. So this is the resistor, this is the inductor, and let me apply a sinusoidal voltage source VT across this combination of R and L. Right? Now, we all know if I write in instantaneous term, VT will be equal to VRT plus VLT. That is, this voltage will appear across the resistive part and the inductive part. Now, if I want to write in the phasor form, what I can write? The phasor source voltage V will be equal to the phasors voltage across resistance, and it will be equal to the phasor voltage across the inductance. Now, you have already derived what is the phasor voltage across the resistance. It is the current through the resistance, phasor current through the resistance into impedance of the resistive circuit, that is I into R. And what is the voltage? It is phasor I into j omega L. That is, you can write I is equal to R plus j omega L. Okay. So in phasor, the calculation becomes very easy. Why we use phasors? Because phasor addition and subtraction can be done directly on the graph. The angles, if I'm doing the division, I can just take the difference of the angles. If I'm doing the multiplication, I can just add the angles and multiply the magnitude. So V is equal to I R plus j omega L. Now, as you already know, V upon phasor I is equal to Z. That is, phasor V is equal to Z into phasor I. So for this circuit, phasor V is equal to phasor I into Z. It implies the impedance of an RL circuit will be equal to R plus j omega L. Wonderful thing. That is, if I combine, earlier you have seen that the resistance has a purely real number as the impedance. The inductance, for inductance, the impedance was purely with j, that is the imaginary part. But if I combine both of them,
then the impedance come out to be R plus J omega L. Now let us see how can I draw the phasor diagram for this circuit. That is, I need to draw the phasor relationship between the voltage across this R and L, that is the source voltage, and the current through the circuit I. Now, again, I am taking I as the reference phasor. So if I take I as a reference phasor, I can draw it like this. This is my I. It will have an RMS value. Since it is, I have taken it to be the reference phasor, I say this is I angle 0. Now, the applied voltage is a summation of the voltage across the resistance and the voltage across the inductance. So, what will be the phasor representation? So, VR will be equal along IR. So, VR, this is your VR. It will be along the reference phasor IR. See, I into R. That is the direction of VR is same as the direction of the phasor I. Now, what is VL? VL is I J omega L. That is direction of VL is same as the direction of J into I. That is what will be the direction of J into I. Phasor I rotated anti-clockwise. That is the direction. Direction of phasor I is this. And if I rotate it anti-clockwise by 90 degree, the direction becomes this. So this will be the direction of phasor VL. So this is VR. Now in VR, I need to add VL. So this is your VL. VL is equal to I into J omega L. Now, this plus this is equal to V. That is, we move from this point to this point, this point to this point, or I can say I move directly from this point to this point, and this is equal to the voltage V. So, this is the voltage V applied across it. So, V is equal to I into Z. So, what is the diagram? This is your VR, phasor VR. This is equal to, this is in the direction of I. This is your phasor VL. It is in the direction of J into I omega L. And if I add both these phasor, I will get the source voltage V is equal to I into Z. If I divide by I both the sides, I will get a new triangle. This triangle is formed by three terms R, J omega L, and Z. And you no need to write J over here because we are writing the magnitude. J indicates the direction. So Z is equal to modulus of Z is equal to under root R square plus omega L ka whole square, which is true as we have already derived Z is equal to R plus J omega L. Now look here, there is a phase difference between the resistive part and the impedance Z, and this is theta. This theta is called impedance angle. Also look here, this is the applied voltage. This is the direction of applied voltage across the LC circuit. This is the current. So the phase displacement between the current through the inductor, through this RL combination, and the voltage across this RL combination, this is also theta because impedance triangle is derived from the above triangle. So this theta is the phase difference. What is this? This is the phase difference. How do you calculate this theta? How do you calculate this theta? So if you look at the impedance triangle, you will get tan theta is equal to omega L by R, or theta is equal to tan inverse omega L by R. So in this way you can find. Now can anybody tell whether an RL circuit, which term is lagging and which term is leading? What is the phasor relationship between voltage and current in an RL circuit? Can anybody tell? Look here, this is your voltage. This line is your voltage and this line is your current. So if you look in the anti-clockwise direction, your current lags the voltage by an angle theta, and theta is equal to tan inverse omega L by R. So got my point? So RL circuit is basically a lagging circuit in the sense that the current through the RL combination lags the applied voltage by an angle theta, where theta is equal to tan inverse omega L by R. Now come to the RLC circuit. Okay. So this sinusoidal voltage source is applied across the combination of R, L and C in series. So the phasor sum, the phasor sum of Vs, yeah, the phasor voltage Vs will be equal to the phasor sum of voltage across R plus phasor sum of voltage across L plus phasor sum of voltage across C. So what is the voltage across R? The voltage across R is, we have already studied, I into R. Okay. What is the voltage across L? The voltage across L is phasor I into j omega L, right? And in a similar manner, the voltage across VC will be equal to the phasor I upon j omega C, where j is the operator which rotates any phasor by an angle of 90 degree. Now the same equation I can write it that IR plus I j omega L, j square multiplying numerator and denominator, and j square is equal to -1. So we will get I upon omega C into j. That is Vs is equal to IR plus ji omega L minus ji 1 upon omega C. Okay. Now let us draw the phasor diagram. Again, taking I as the reference phasor. I is equal to I angle 0. I take it as a reference phasor, right? So let this is be the direction of I. So this is my phasor I. Okay. Now what we have to do? We have to add phasor VR. We have to add VR plus VL plus VC. So let us draw phasor VR. Phasor VR is I into R. That is the direction of VR will be same as the direction of IR. So let it be. Not able to change the pen. Some lag is there going. Okay, let it be. I'll draw with the same ink. So let it be VR. So VR will be having the same direction as that of IR. Now what we have to add in VR? We have to add VL and VR. What is the direction of VL? The direction of VL is
J multiplied by the direction of I. That is anti-clockwise. This is the direction of VL. Okay. VL is equal to I into J into omega L. Now, what will be the direction of VC? It is minus J. So, I is in the horizontal direction. So, minus J direction will be clockwise 90 degree. So, this will be the direction of VC. VC is equal to minus JI into 1 upon omega C, right? So we have to add three phases. So let us first add vertically. So VL and VC are in opposite direction. They can have equal magnitude. It may be possible VL is greater than VL, and it may be possible that VC is greater than VL. So let us take, for instance, VL is greater than VC. When will be VL greater than VC? When XL is greater than XC, right? So this vector will be equal to VL minus VC. That is, I have subtracted the length of VC from VL. So this is VL minus VC. So this vector plus this vector will give you the applied voltage V, which will be equal to I into Z, right? And this is the angle theta. So if I say Vs is equal to I R plus J omega L minus 1 upon omega C. Now, if I compare the expression, Vs should be equal to Yi into Z. Yes or no? So, Z for an RLC circuit will be equal to R plus J omega L minus 1 upon omega C. Now, case 1, if VL is greater than VC, you get this phasor diagram, and from this phasor diagram you can clearly see that Vs is ahead of the current I by an angle theta. That is, the voltage across this combination leads the current through the combination by an angle I, and that angle, the same is the impedance angle. Yes or no? This is R. This is omega L minus 1 upon omega C. Just divide by I. And this is your Z. This is the impedance angle. So V leads I by an angle of tan theta is equal to omega L minus 1 upon omega C upon R. Now just imagine case 2. If VL is less than VC, that is the magnitude of VL is less than the magnitude of VC, then what will be the thing? So this is your VR, this is your I reference phasor in the same direction, this is your VR. Since VL is less, the net vertical sum will be downwards. This will be VC minus VL. So this plus this should be equal to V. So this is V is equal to I into Z, and this is your angle theta. Now look here. In the second case, if VL, magnitude of VL is less than the magnitude of VC, the voltage phasor is behind the current phasor in anti-clockwise direction. That is Vs lags I. Similar to that is, if the voltage across inductance or the inductive reactance is greater than the capacitive reactance, your RLC circuit behaves like an inductive circuit. That is, in inductive circuit, as you have seen, the current lags the voltage by an angle theta. And if VL is greater than VC, if VC is greater than VL, then your circuit will behave like a capacitor circuit. And in both cases, the impedance will be equal to Z is equal to R plus J omega L minus 1 upon omega C. Okay, that is that is right. That is, in an RLC circuit, in an RLC circuit, RLC circuit, there are two cases. VL is greater than VC, or I can say XL is greater than XC. In this case, the current lags Vs, and in the second case, if VL is less than VC, that is XL is less than XC, then the current leads Vs. That is, this circuit behaves like an inductive circuit, and this circuit behaves like a capacitive circuit. So the combination of R, L, and C can both behave both like an inductive circuit and a capacitive circuit. So this is the impedance diagram for the case when XL is greater than XC. We have drawn it at the back, and this is the instantaneous voltage diagram. So we have reached to the combination of RLC circuit, and we find that in an RLC circuit, the impedance depends on R as well as omega L and omega C. Now we will study the resonance in the series RLC circuit, and then we will similarly derive the expression for the resonance in the parallel RLC circuit. Now, what is resonance? Now, resonance, I have earlier said, when your driving frequency is equal to the natural frequency in terms of an electrical circuit. The two most important thing for the resonance is that you should have a two independent energy storage elements to so that they can exchange energy from each other. So if we see the RLC circuit, then I have two energy storage element, that is, one is inductor and one is capacitor, which can exchange the energy between them. And the resonance phenomenon is not limited to the electrical circuit, it is limited to any other circuit also. Suppose if I have a mechanical system having a spring and mass, suppose you tune the radio station, what do you do is that the radio station is broadcasting a particular frequency, and what you would do is that you tune your frequency to that particular radio station. That is, the driving frequency is equal to the natural frequency. Your frequency matches the frequency of the station, and then the signal is amplified, and that phenomenon is called the resonance. Similarly, just imagine we are walking on a bridge. So, if the frequency of the bridge matches the frequency of your footstep, the vibration may be so low, so high that it can damage the bridge structure. So, resonance can be a constructive phenomenon, resonance can be a destructive phenomenon. Resonance basically is occurs when the driving frequency is equal to the natural frequency of the system, and it is characterized by the increase in certain parameters, which and that property can be used as to make the circuit as an amplifier wherever needed. So what happens at a resonance, if I talk in terms of electrical circuit, at resonance in a steady state, when the driving frequency is equal to the natural frequency of the system, the steady state response is in time phase with the source. Do you remember in which circuit the steady state response was in time phase with the source? We have studied R circuit, we have studied L circuit, we have studied C circuit, we have studied RL circuit. On a similar manner, we can study RC circuit. We have seen the analysis of RL circuit. So in R circuit, both voltage and current are in same phase. That is, at resonance, your circuit will behave like a resistive circuit, that is, your source and response will be in the same phase. So in inductive circuit, what was in inductive circuit, there was a phase displacement of angle theta given by theta is equal to tan inverse omega L by L. So that theta, the current lags the voltage by an angle of theta, or you can say the voltage leads the current by an angle of theta. That is, the source and the response were out of phase by an angle theta. In a similar manner, in a capacitive circuit, the source and the response were out of phase by an angle theta, and the same story goes for RL, RC, and an RLC circuit. So, we have discussed this earlier. In an RLC circuit, I have two energy storing element. One is inductor, which stores the energy in magnetic field. Other is the capacitor, which stores the energy in the electric field. We have already seen the inductive reactance is equal to XL is equal to J omega L. Now, if I plot XL with respect to the frequency, you will see it is a linear function of the frequency, and hence I can represent XL by a straight line. In a similar manner, if you want to plot XC with respect to the omega C, it is an inverse function of the frequency, and hence the parabola is like this. Now, the inductive reactance is directly proportional to frequency. So, XL increases with frequency, and the capacitive reactance is inversely proportional to the frequency. So, it decreases with frequency. Now, what we said is that at resonance, the source and the response are in time phase with each other. And as you have looked at the circuit, the time phase, that is the phase difference was initiated by the j term of the impedance. That is, suppose the impedance is R plus J XL minus XC for this RLC circuit, right? Now, when this RLC circuit, what will be the condition when this RLC circuit will behave so that the voltage is in time phase with the current? So it should behave like a resistive circuit. Only there the voltage and current are in phase with each other. What does it mean? It means that the imaginary part of the impedance should be equal to 0. So for resonance condition, the impedance should be purely resistive, or the imaginary part of the impedance should be 0. That is,
minus XC should be equal to 0 at omega is equal to omega 0, where omega 0 is the resonant frequency of the system. Now, when we apply this condition, XL is equal to omega 0L, XC is equal to 1 upon omega 0C, and here we come to see that the resonant frequency is equal to omega 0 is equal to 1 upon under root LC. What does it mean? It means that when the driving frequency of the source Vs is equal to Vm sine omega t becomes equal to the natural frequency of the circuit, which is 1 upon under root LC, the system resonates, and omega 0 is called the resonant frequency of the system. Now see one interesting thing, that the resonant frequency only depends upon the energy storing elements of the system. It is not depending upon the resistance R. That is, the energy will oscillate in between the inductor and the capacitor. That is, the energy will oscillate between the two energy storing element, and R only act as a damping component. That is, it act to damp the oscillations, that is the change of energy, exchange of energy between L and C. Therefore, the resonant frequency does not depend upon the resistance of the circuit. It only depends upon the energy storing elements of the circuit, and that's what we have said, that there must be at least two energy storing element in the circuit which are capable of exchanging the energy. Now look, what is the effect of increasing omega on the current? Now this is the expression for the current. I is equal to V upon R plus J omega L minus 1 upon XC. Now suppose I go on increasing the frequency omega of the source. So how does the current changes? Now if you look here, if I change the frequency, what is your Z? Z is equal to R plus J omega L minus 1 upon omega C. That is, Z can be written in terms of magnitude. What is the magnitude? Under root R square plus omega L minus 1 upon omega C ka whole square, angle theta, where theta is equal to tan inverse XL minus XC upon R, or you can say it is equal to tan inverse omega L minus 1 upon omega C upon R. ठीक है? Now look here. Change in frequency means if I changing the frequency, I am changing the magnitude as well as I am changing the phase angle of the impedance. Now, when omega is close to 0, when omega is close to 0, the capacitive, the inductive reactance is 0, omega L is equal to 0, but the capacitive reactance is almost infinity. Hence, the current magnitude approaches 0. The impedance, this graph shows the impedance. Okay. So, for small frequency, omega L is 0, that is near to the 0, and the 1 upon omega C will be infinite. Therefore, the impedance will be maximum and the current will be minimum. So, this is the current. Now, as you go on increasing the frequency, the reactance part of Z decreases, thereby causing an increase in the current. And do you remember at resonance, that is at
omega is equal to omega 0, the impedance Z was equal to R. Why? The impedance Z was equal to R because the reactive part was equal to 0. It means the impedance was minimum at the resonant frequency omega R. Now, since the impedance was minimum at the resonant frequency omega R, the current would be maximum, and the maximum current is given by the expression V upon R. Now, as omega continues to increase beyond, as omega continues to increase beyond the resonant frequency, what happens is that the impedance again start increasing and the current starts falling. What is happening is that if you look at the expression of the impedance at the resonance, the circuit is behaving like a completely resistive circuit, that the current and the voltage are in phase with each other. Below the resonant frequency, since the capacitive reactance is large, the, the circuit behaves like a capacitive circuit, and above the resonant frequency, the circuit behaves like a inductive circuit because as omega increases, the omega L continues to increase. So below the at resonant frequency, circuit behaves like a completely resistive circuit. That is, your voltage and current would be in phase with other. Your current would be maximum. Below the resonant frequency, your circuit behaves like a capacitive circuit, and above the resonant frequency, XL dominates over XC, and therefore the circuit behaves like a inductive circuit. Now, this point is of prime importance, that is the peak of the resonance curve. Now we want to see how wide is my resonance curve, that is the width of the resonance curve. How do we measure the width of the resonance curve, and why do we measure the width of the resonance curve? We measure the width of the resonance curve by two frequencies. Let us say the frequency F1, this is my frequency F0, this is my frequency F2. Okay. Now, how these frequencies are defined? These frequencies are called the half power point frequencies. The F1 and F2 are called the half power point frequency. Now, as the name indicates, half power point frequency, what does it mean? At resonance, what is the power? At resonance, the impedance of the circuit is Z is equal to R. So what is the power delivered to R? R is equal to current as resonance whole square into R. And I will write this as P0. That is, power delivered to the resistance at resonance is I0 square into R. Now what will happen is the half power point. At half power point, we define the frequencies as those frequencies where the power delivered to R will be half of the power that is delivered to R at the resonance. That is, at frequency F1, the power delivered to R will be I1 square R. At frequency F2, the power delivered to R will be I2 square into R. And this power will be half of the power that is delivered to the R at resonance. Now, looking at the expression, if P1 is equal to P2 is equal to P0 by 2, this means I1 should be equal to I2 is equal to I0 by 2. So, at resonance, the current is I maximum is equal to I0. At half power point, the current will be equal to I0 by under root 2, right? And the width of this resonance curve is given by omega 2 minus omega 1. Now, how to determine this omega 2 minus omega 1? Now, at half power point, since the current is 1 by under root 2 times the current at the resonance, the impedance will be under root 2 times the impedance at resonance. The impedance at resonance is under root 2 R. Now, at half power point, replace Z by under root 2 R, square both the sides. So that is what is the impedance for you? Replace Z by under root 2 R. So if you replace under root 2R, this will be 2R square. R square plus omega L minus 1 upon omega C ka whole square. So this will yield a quadratic equation. And the quadratic equation, if we will solve, minus b plus minus under root b square minus 4ac upon 2a, this will give you omega 1 and omega 2. And if you solve due to limitation of time, I have planned to do this derivation on the screen, but due to the limitation of time, just it is a simple quadratic equation you can solve. So omega 1 will come out to be this, and omega 2 will come out to be this, and omega bandwidth will become out to be 2 alpha, where alpha is equal to R by 2L. That is, the width of the resonant curve will depend upon the ratio of R and the ratio of L. It is not depending upon the capacitance. Look here. That is, if R is small, the width of the resonance curve will be small. And if R is high, the width of the resonance curve will be more. Now, do you want a small, narrow width of the resonance curve, or narrow, or the wide resonance curve? Which one would you prefer? Now look here. Now look here. Resonant is a frequency selective phenomenon. Now, if you have a narrow resonance curve, that is the narrow curve, then the frequency is sharp, the range of frequency is less, the tuning will be fine. Now, if your resonance curve is the wide curve, the range of frequencies between the half power point will be more, and your tuning will not be very fine. Okay. Now, the selectivity of the circuit is defined by two parameters. One is bandwidth and the other is quality factor. Now, what is selectivity? How do you define the selectivity? Selectivity is the ability of the circuit to reject all the frequencies except the resonance frequency, right? And the quality factor is defined at omega 0 upon omega bandwidth. Omega 0 is the resonant frequency. The bandwidth we have derived, it was equal to R by L. So, the quality factor is given by omega 0 L by R. Now, this is in terms of the parameter of the circuit. In terms of energy, the quality factor is defined as the total energy stored. What is the total energy stored? Total energy stored is half Li square plus half Cv square.
and the energy dissipated per cycle. That is, what is the energy dissipated? The energy will be dissipated in the resistance. So what is the per cycle? The energy is dissipated. This is a very fine definition of quality factor, which is in terms of energy, and it is applicable to any resonant system regardless of the composition. That is, whether it is an electrical circuit or whether it is a mechanical phenomenon. Quality factor is equal to the total energy stored upon energy dissipated per cycle. Now, what do we need to have a good selectivity? We always want a fine selectivity. We need to have a low bandwidth and we need to have a high quality factor. Why we want to have a high quality factor? Because then the energy dissipated per cycle would be very less, and the bandwidth should be less. That is, the peak should be very narrow, so that the ability of the system to reject all other frequency, basically all other frequency comes the takes care into the frequency band between the half power frequency. That is, the bandwidth should be less and quality factor should be high for a highly selective circuit. Now look here, look at this graph. If you will see, this graph is drawn for three quality factors. uh, Q1 is less than Q2 is less than Q3. So lesser is the quality factor, broader is the graph, and wider the bandwidth of the resonance is very large and the selectivity is low. So higher the quality factor, lesser will be the bandwidth and higher will be the quality selectivity of the system. Now see, now let us see what happens to the voltages at the resonance. Now this was your RLC circuit. At resonance, omega 0 is equal to 1 upon under root LC. What was the current? Current was maximum since the impedance was minimum. So current will be, phasor I would be equal to phasor V upon R. Now let us see the voltage across the inductor. So voltage across the inductor will be equal to the current through the inductor into XL. So voltage across the inductor would be VL. What is the current through the? It is V angle 0 upon R into J omega L. So VL is equal to the magnitude. Let us take the magnitude. Magnitude of VL will be equal to the magnitude of V, that is, VL phasor can be written like this. What will be the VL phasor? The magnitude of V into omega L upon R angle 90 degree. So the magnitude of VL is equal to V omega L by R, or you can say it is equal to Q. Omega L by R is equal to Q, and V is the RMS value of the source voltage. And this is the quality factor of the circuit at the resonance. So it is Q0 into V. Now look here, the magnitude, that is voltage across the inductor, is amplified by a factor of Q0. That is, you applied a source voltage of V and the voltage across the inductor is amplified by a factor which is the quality factor. Now what is the angle of this? The angle of this is plus 90 degree. So if the current as the resonance is taken at the phasor, this is your I0. So this will be your VL 90 degree. Okay. In a similar manner, if you will see, what will be VC? VC will be equal to I, the current flowing through the resonance this is at resonance, V is 0 and VC 0.
So VC0 is equal to I into XC, and I will be equal to V upon R into 1 upon j omega C, and this will be V upon R omega C. J 1 upon j will be equal to minus 90 degree, and since you know at resonance omega L is equal to 1 upon omega C. This was the condition of resonance. So replacing omega C, 1 upon omega C by omega M. So you will get V omega L by R angle minus 90 degree. That is, the voltage across the capacitor is also amplified by a quality factor. So, but the phasor direction of the capacitor voltage is in minus 90 degree. That is, the phasor direction will be downwards. That is equal to VC. So VL and VC are opposite to each other in direction. They are equal in magnitude, or you can say at resonance, there is a magnification of voltage across the two elements, that is across the inductor and across the capacitor. However, both of them cancel each other because both have an opposite direction. Magnitude is equal and the direction is opposite. So the phasor addition will contribute to zero, and hence the only voltage, the circuit behaves like your capacitive voltage. So the characteristics of the series RLC circuit at resonance is it has a minimum resistance, that is your current is maximum. So it is called an acceptor circuit. The voltage across the capacitor is equal to the magnitude of voltage across the capacitor is equal to the magnitude voltage across the inductor, and both of the magnitude are amplified by a quality factor, that is it is equal to Q into the magnitude of the source voltage. And of course this is the resonance condition, that is XL should be XC at the resonance, because we have defined resonance as the steady state response when both the source and the response are in time phase with each other. That is, both the voltage, which is the source, and the current, which is the response, are in time phase with each other. That is, the circuit has to behave like a resistive circuit. And if the circuit has to behave like a resistive circuit, then the imaginary part of the impedance should be equal to zero. When the imaginary part, which is in this case, of the series resistance R is equal to Z is equal to R into J omega L minus 1 upon omega C. So XL is equal to XC. In a similar manner, we can study the resonance in a parallel circuit. In a parallel circuit, we take the source to be the current source and we measure the response to be the voltage across the resistance, inductance, and the capacitance. Just to ease the calculation, we write the expression for the admittance of the circuit. Now, the admittance of the circuit impedance is equal to Z plus R J X, where R is the resistance, X is the reactance. So what is J? G is equal to 1 upon R. It is the conductance. You all know this basic physics. And what is B? This is the susceptance of the circuit. It is equal to 1 upon X. So it is equal to 1 upon R j omega X minus 1 upon omega L. Again, at the time of resonance, your source and the response should be in time phase, and we have studies that they should be in time phase only when the circuit behaves like a resistive circuit. That is, your impedance should only have a real part, there should be a no imaginary part. That is, the imaginary part of the susceptance should be equal to 0. So we have placed this susceptance equal to 0. So again, you will find whether it is a parallel circuit or whether it is a series circuit, the natural frequency of the circuit comes out to be omega 0 1 upon under root LC. Now let us see what happens to the bandwidth of the circuit. Now here, look here admittance is maximum. Why admittance is maximum? Admittance is G plus JB. Admittance is minimum, not maximum. If admittance is minimum, impedance would be maximum, and it will be equal to Z is equal to again R. Again, you can see the bandwidth of the, what is the source? The source was the current source over here. What is the response? Response was the voltage. So at resonance, the voltage is the maximum, which is equal to I into R. Just you have to replace everything, replace current by the voltage in a parallel resonant circuit. That is, the response is here is now the voltage. Now again we can calculate the bandwidth in a similar manner we have calculated earlier. That is, these are my half power points. That is, at these points, power delivered to the resistance is half of the power delivered to the resistance at resonance. So the omega bandwidth will be, comes out to be 1 upon RC, and the quality factor, which is equal to omega 0 upon omega bandwidth, will be equal to omega 0 RC. Remember, in an R series RLC circuit, it depends upon, for a series RLC circuit, Q0 was omega 0 L by R. For a parallel circuit is equal to omega 0 R into C. So it is never good to define quality factor in terms of the parameters. We always define quality factor in terms of the energy. So in terms of energy, again, we have already defined and the expression remains the same. Quality factor is equal to total energy, 2 pi into total energy stored upon the energy dissipated per cycle. So I intend to do few numericals also from this topic. So I saw somebody missed the initial lectures. They were asking why we are studying resonance for this. So initially I have told you that we have a qubit, then we excite the qubit via microwave. This microwave has certain frequency nu, let nu or f. And what is the principle is that if I want to transit from energy level 0 to energy level 1, the microwave frequency, the input microwave frequency should match the transition frequency, that is h nu should be equal to the energy of the microwave pulse should be equal to the transition energy between 0 and 1. And as you have always seen that a resonant circuit act as a selective circuit, that is, for a resonant circuit, you can exclusively identify the resonant frequency, and by maintaining the bandwidth lower and by maintaining the quality factor very high, you can just make the circuit selective for a particular frequency, and then the same circuit can be used as an amplifier. The same circuit is used, LC circuit is used for measurement of the quantum state. We just couple an LC circuit with the qubit and we measure the resonant frequency. If qubit has an effect on the resonant frequency, that is, if the resonant frequency deviates, then it means that the qubit is in some quantum state. If the resonant frequency is same as that of the LC circuit, it means that your quantum state of the qubit is the zero state. So this is all about the resonance. And if I get a time, we can complete the numericals. We can take the numericals tomorrow just to see the effect, how the resonance is affecting the resonance is both for the series RLC circuit and for a parallel RLC circuit. So basically L and C, you can say it is in parallel. And the energy fluctuate between L and C. So if you combine L and C, so energy, the capacitor charge and discharge, and it exchanges its energy through L. So maybe in some quantum hardware course, you will realize the qubit. I have taken a very small section on the qubit and the effect of resonance. In the earlier slides, you can go to the earlier slide. Those who have missed the earlier slides, you can see how resonance is related to the quantum theory. Now, in the next lecture tomorrow, we will study the traveling waves related to the quantum technology. We are really sorry for the few disturbance at the early of the internet issues. However, if you face any issues, you can directly mail me at dsaxena dsacena.ee@mnit.ac.in. So this is all about the resonance. So thank you very much, and we will continue tomorrow at the same time. One question is there, how do we realize qubit in the case of LCR circuit? Consider LCR circuit as L is never ideal. L always have I'll always have some damping associated, some loss associated with it. So R has no role. You have already seen the resonant frequency is 1 upon under root LC. So resonant frequency R is not resonant frequency is not affected by R. The purpose of R is only to damp the oscillations. So you can only take the simple LC circuit. So qubit is realized by a simple LC circuit, but R is always a part of an LC circuit because an inductor is never an ideal. Always a loss is associated with it. So thank you very much. हाँ, question कल करेंगे.
Thank you.
हमारे में क्यों नेट खराब हुआ? म्यूटेड है